Hello and welcome. Today we're going to be using the continuity equation to determine the rate of growth or decline in an interval region. Alright, so let's recall what the continuity equation is all about. What we really mean here is the integral form. The integral form of the continuity equation. And what we're going to also assume no sources. So in this particular case, the continuity equation is written this way. So let u of x comma t be some density, okay, and u in some interval a to b is going to be the total mass in the region, okay? And we're also going to have a flux rule, and this flux rule is going to be this: u minus 2 partial derivative of u with respect to x. Right, so here we have an advection term, and here of course we have a diffusion term. Okay, so this together is our flux rule. Okay? And at t equals 0, we have the following graph. So there's our graph. And what I want you to notice here is the slope is about 1. And here the slope is near 0. Okay. And in fact, maybe we'll just clarify on the graph that the slope is essentially 0. All right, so from here we should be able to figure it out. The slope is about 1. We'll make those unit lengths right there. The best I can do, sorry about that. Okay, so we're going to use now, so we have to use, so the answer goes like this. What we have here is use the continuity equation. du, capital U dt, is going to have to be equal to phi A minus phi B. All right, so we're going to have to estimate phi A and then phi B. So phi A, well, that's going to be equal to u minus 2 ux, the derivative, right? So that's going to be approximately equal to, well, the value of u is equal to 1, right, minus 2 times 1. All right, so, and of course that was our estimate for the slope there, so we're going to have a flux of approximately negative 1. Okay, great. Now let's try phi of b. Let's figure out what it is about. It's going to be u minus 2 ux, and that's going to be, of course, 3 minus 2 times 0, so that'll be equal to 3. All right, so this is going to be negative 1 minus about 3. So that's the approximation. So it's going to be negative 4. That says then that basically du dt is of course negative. So we're going to conclude that it's shrinking. Okay, so that right there is the conclusion to the first problem. Okay, So the question, of course, was, I didn't even write the question, and I'm sorry about that. We want to know, what is the sign of du dt? We want to know, is it less than or equal to 0? Okay, so what we want to figure out is that question, so we have an answer. All right, now the follow-up question we have for it. So the follow-up question is, find the PDE associated with the flux rule. So for this, we use the continuity equation in differential form. So that's going to be the partial derivative of little u with respect to t is equal to the partial derivative in space of the flux rule. So the flux rule in this particular case was u minus 2 partial derivative of u with respect to x. So the problem is simply to plug this in. So this is a follow-up question. It just shows that you understand what the continuity equation is for, and how you essentially can build PDEs from the continuity equation and a flux rule. Okay, so I hope this video showed you two examples, two different problems that are very common on exams that I write, related to how the continuity equation works with the flux rule, and how you can use it to determine the dynamics of the amount of a conserved quantity in a region. Okay, I'll stop there.